I'll give you another example. Let's talk about baroreceptors, or how the blood pressure is regulated. So supposing your blood pressure for some reason rises over there. So maybe you started exercising, or you started or you are just about to enter the examination hall, and you're a little excited and scared, and it is most likely that your blood pressure will rise just a little bit. So you have sensors that sense your blood pressure and that monitor your blood pressure in the carotid vessels and in the aorta, and those organs are going to sense the stretch on the vessel. In response to how much of stretch there is, it knows that there is more blood pressure, because the more blood pressure you have, the more you stretch your vessels. So that level of stretch is sensed by these sensors, and it gives signals to the integrating system, which is in your brain, in your brainstem. And we'll be doing this in the cardiovascular chapters when we go there. But anyway, so the integrating system is now going to see, okay, the blood pressure right now is a little higher than my normal set point, which I would like it to be, so I have to do something. Then a signal is given via effector organs to the effector organs, and it's going to cause some changes in the way your organs are working to lower the blood pressure back to normal. Usually it would try to slow down the heart rate and maybe even cause a little dilation of vessels. So this is how your blood pressure is regulated over there. So this is an example, a classic example of negative feedback, where you are opposing the change of deviation. So what is a negative feedback doing actually? It's opposing the direction of deviation of the variable, opposing the direction of deviation, like in the example of blood pressure which I just gave you. And if we look at positive feedback, it is different in that this is actually a system that's going to increase or aggravate the deviation of the variable. Now, is that a good thing? Sometimes, not always. You see, positive feedback systems actually could either be a vicious cycle or a virtuous cycle. So I'll explain about this in some time. So virtuous cycle, virtuous meaning good, and you also have vicious cycle. A positive feedback system is where you do have a sensor, an integrating system, and an effector organ. And now what happens is a certain change takes place. And this change is actually going to be picked up by the sensor, and now the integrating system is going to actually cause more of this change to take place. So the effector signal is going to cause further change, further deviation. You are not restoring the parameter back to normal, maybe because that is necessary for the body in some cases. So I'll give you an example of positive feedback. When we speak about positive feedback, some of the best examples are when you injure yourself and you start losing a little blood, like you're shaving and you just cut your face and there's a little bit of blood coming out of your face. Now luckily we have some mechanisms in the body to clot the blood. This is called your hemostatic mechanisms, and in that you will realize that there are certain clotting factors that activate more clotting factors that finally make sort of meshwork of a protein called fibrin from fibrinogen. So these clotting factors are like inactive enzymes, and one enzyme activates another enzyme that activates another enzyme that activates another enzyme, and these enzymes are, one enzyme does not just activate another molecule, it activates 10 more molecules, and the other one, the other set is going to activate 10 more and 10 more. So you're getting this exponential rise in a change taking place over here. So this is hemostasis, meaning it's a part of blood coagulation taking place. And so your positive feedback is very important for certain situations like hemostasis. There are other good examples of positive feedback. I'll give you another example, like giving birth, the parturition reflex, also known as the Ferguson reflex. So Let's just give some examples of positive feedback. Ferguson reflex, positive feedback. You have Ferguson reflex. When it's time to give birth to a baby, now you're aware that babies, they hang upside down in the womb over here, and when the time comes at around 9 months, the baby starts to descend into the cervix, and eventually with some triggering factors you initiate labor. And as this baby's head is going down into the cervix, nerves and neurons will sense this kind of pressure and stretch that is taking place on the cervix, and it would give the signal to your hypothalamus. And this hypothalamus is going to cause the release of posterior pituitary, from the posterior pituitary hormone, the release of oxytocin, a hormone called oxytocin. Now this oxytocin is going to go to your uterus and cause contraction of the uterus. Now as the uterus contracts, it's going to push this baby down even more, and its head is going to further stretch the cervix even more. And this stretch on the cervix is going to cause even more signals to go back up over there. So the sensor is these neurons, and they are going to sense this stretch on your hypothalamus, and that it's going to give the signals to the hypothalamus, and that's going to cause the release of more oxytocin, more contraction, and more stretch on the uterus. So see, this is a self-propagating type of cycle. It's going to keep making the signal much stronger as the baby keeps adding more pressure, and this keeps going on until the baby's out, until the fetus has been delivered, until the baby's been delivered over here. So this is an example of a good example of positive feedback over here. Then, like I said, hemostasis. Then if you look at other things like luteinizing hormone surge, what is that? So if you remember, in the female menstrual cycle, we have a hormone called luteinizing hormone that raises its level by the 14th day of the cycle. What happens is, as the estrogen levels are rising through the cycle, the luteinizing hormone levels rise even more, and that's going to cause even more estrogen, more luteinizing hormone, more estrogen, more luteinizing hormone. So this is your luteinizing hormone surge. It's a good example again of positive feedback, which is necessary. Then you have other examples like lactation, where if a baby starts suckling on his mother's breast, then the neurons from the breast, the sensors are picked up by the mechanosensors. It could sense the baby's tongue that is moving over the areola of the nipple, and that is going to cause signals that go to the hypothalamus and again release oxytocin, and this oxytocin is going to cause further contraction of smooth muscles in the breast, causing more milk to flow into the baby's mouth. So that's another thing. Then we have the generation of action potential. Action potential is how your neurons communicate with each other, and some excitable tissues also. That's how they send signals to each other. So action potential, it's a very big chapter in its own, and we'll be talking about it. I just want you to know that sodium ion channels open up, and sodium enters into the cell, changing the voltage inside that cell. And this sodium entering into the cell makes even more sodium channels open up, because they're sensitive to that positive voltage. And that causes even more channels to open up, and that causes even more sodium to enter into the cell. So if we have some sodium channels over here, this is the cell membrane I'm drawing, and these cylinders represent sodium ion channels. When sodium enters inside the cell, it makes the surrounding area positive. So we have positivity, and now this positivity is going to cause the next sodium channel to open up, and more sodium can enter in the cell, and then more sodium enters into the cell, and more sodium enters into the cell, like so. So this is an example of this one, positive feedback, and this cycle of sodium causing more sodium to enter is called the Hodgkin cycle. It's called the Hodgkin cycle. There was a lot of work done by Hodgkin on action potentials and membrane potentials. Hodgkin, Huxley, and other people we'll be speaking about in the next chapter. Then we have your the other concepts like calcium-induced calcium release. So this is where this happens in your heart muscle, in the myocardium of the heart. So what happens is when you look at your heart, action potentials that give signals to the heart muscle to contract, they go all the way down into the cell. There are these deep fissures over there in the cell membrane that exist, which carry a signal deep inside the cell. And now what happens is there are special little channels that exist over here, and calcium enters through one of these channels and falls upon the other channel over here, what we call the T-tubule. This is called the T-tubule. It's like a little well in the muscle structure. And then what happens is you have your little L-tubule, T-tubule and L-tubule. Your L-tubule is your smooth endoplasmic reticulum over here in your cell. And when the action potential goes down the T-tubule, calcium is sprayed upon the L-tubule, and inside your L-tubule you have even more calcium, and this calcium falling upon the ion channels is going to cause even more calcium to be released over here. So you get a little calcium triggering a big release of even more calcium. So that's why it comes under positive feedback. Then you have your feed forward mechanism. Feed forward. Now, feed forward mechanism is another important concept. When we speak about feed forward mechanism, it is a kind of system where it's able to predict what's going to happen. It's able to predict a change. It predicts a change before it even happens. So what does that mean? I'll give you an example. Imagine, look at your body. You have your vital organs inside your chest and head, with your heart, your lungs, your brain. All of this is important for life. Now, you have your limbs on the outside, you have your outer skin on the outside over there. Now, what happens is whenever there's a change in the temperature, in the ambient temperature, then what's going to happen is your body will exchange energy with the surrounding environment. So if you go into a cold area, you start losing heat to the external environment. And if you go to a warmer area, you start gaining heat from the external environment. So let's take an example of you suddenly leaving a nice warm cozy cottage in a winter highland mountain over there, and you go outside leaving the cozy warm room with a nice fireplace, and now you go out into the cold without a coat. Suddenly you're blasted by cold air from around. So there's a lot of cold air, and it's going to start cooling your body over here. So the first thing that gets cold is your shell body. The shell temperature drops over there. Now this is the first thing. This is the part of the body that's more exposed over there. Your internal organs still have enough heat and to maintain their vital functions. They've not yet been affected so much, but eventually, if we don't do something, the core organs are going to start getting cold, and then we're going to have some problems. So the core temperature has not yet changed because you just left the room, but imagine if it's reached to that point. So our body is able to make changes in response to changes that take place in the shell body temperature. The minute your shell temperature falls, the body starts to do things where it tries to raise the temperature and prevent a further drop in the core temperature. So even before your core temperature has been altered or affected, the body has sensed the change in the shell temperature and makes some adjustments in to take place over there. So we start to shiver, we start to change our behavior, we start to reduce our surface area by curling up into a ball. We try to shiver, we start to shiver, and we even try to seek warmth over there. So also vasoconstriction takes place in such situations. So for that reason, this is an example of feed-forward mechanism, where we are able to predict a certain change before it happens over there, and then automatically we are able to make changes in advance. Another example, I'll give you a few other examples of feed forward. Apart from thermoregulation of the body, is something called the cephalic phase of gastric secretion. Cephalic phase of gastric secretion. So what is cephalic phase of gastric secretion? So sometimes you just look at food and you already the acid in your stomach already starts to get secreted over there. So this is a response of our body in response to food, or the anticipation that we are going to eat food. Like if you are just passing by a fancy restaurant with an open grill, and the very smell of the barbecue just goes down into your nose, your body thinks, okay, there's food, and maybe I'm going to get some of that food inside me. So the stomach starts to secrete more acid in response to the very sight, smell, and even sometimes thinking about food can do that also. So this is the cephalic phase of HCl, of gastric secretion. Gastric secretion. Then you have other types of feed forward, like the very thought of exercise. Just thinking of lifting a weight, lifting a barbell, thinking of exercise can cause tachycardia. You haven't even lifted the weight, or even just sometimes passing by your gym, which you work out with your trainer every day, can make a slight increase in your heart rate. So this is an example of feed-forward mechanism. Then you have other things like the cerebellum. It keeps tabs on every little joint and muscle in your body, and so it knows when some dangerous movement is going to happen and adjust for that in advance. So we'll be talking about that in its respective chapter. So this is feed-forward mechanism, and this is how with these systems we're able to maintain the milieu interior and maintain the constant conditions of the internal environment that we have, and keep the parameters in a certain range over there. Now, I'd like to just talk a little bit about these different systems over here and their advantages and disadvantages. Well, the advantage of feedback system, of your negative feedback system or positive feedback, the feedback systems are that you are able to, what do you say, well, it's the most important type of feedback system that exists over there. Most of your control systems in the body are negative feedback systems, and they're the main format in which your feedback systems are organized to bring your various parameters back to normal. But the disadvantages of your negative feedback systems are usually this compensation, the correction is never 100% complete. Okay, it's never 100% complete. So how effective is a negative feedback system? The effectivity, the effectiveness of a negative feedback system, its effectiveness is based on how much is the gain of the system. We can express the effectiveness of a negative feedback system based on what is the gain of that system. So what does gain of the system mean? Gain of a system is, it's a mathematical expression of how effective this negative feedback would respond to a fluctuation or a deviation from your from the normal set point. So it is the ratio of degree of correction that your system does divided by the error that persists, error that the system cannot fix. So degree of correction by error. So the more the correction than the error, the more is the gain of the system. I'll give you an example. So supposing you have normal blood pressure, an average blood pressure of 100 millimeters mercury. And now what happens is I can increase your blood pressure by taking an intravenous, giving you an intravenous bolus sample of normal saline solution. That's just salt water, which I can inject into your veins and expand the fluid volume. By increasing the volume of your blood, I can increase the blood pressure, because you change the volume, you change the pressure. So there is a chance that your blood pressure might rise from 100 to a much higher number. Now, how high is that? Maybe it might rise to 110 millimeters mercury if you are in a normal person, in you, provided you're normal. Now, this blood pressure is regulated by your baroreceptor reflex, and any fluctuation activates the baroreceptor reflex, those pressure sensors in the blood vessels I spoke to you about, and they can adjust your heart rate and eventually alter the blood pressure in your body. Now, supposing you got rid of the baroreceptors, you were able to cut off the nerves that innervate that baroreceptor system. So now no more signals can traverse. So you've effectively eliminated the baroreceptor system. Now, what if I gave you the same amount of fluid after cutting the baroreceptor system? So from 100 millimeters mercury, your blood pressure may rise to, let's say, 130 millimeters mercury. So that means the baroreceptors were able to bring your blood pressure closer to normal by like 20 units. Because if you see, without baroreceptors, the blood pressure rose to 130. With baroreceptors, the blood pressure rose to only 110. So the degree of correction was 20 millimeters mercury. And the error is the amount of error that persists. That's 110 minus 100. That's 10 millimeters mercury. So that comes to 2. So the gain of the system is 2. And this is a good number. All right, this is just a simple example of how blood pressure regulation, we can measure the gain of a system over here. It's just a simple example just to give you a gist of the idea. Now, if there was a negative feedback system which was 100% effective and the error was 0, then if you divide any number by 0, that means you get the number infinity. So this kind of a gain of the system would be infinity. We call this an infinite gain system. And they really don't, there are very few infinite gain systems that exist in the body over there. So mostly you should think of the kidneys, how they function. Kidneys are very effective in maintaining homeostasis. If you ever speak to a nephrologist and say, maybe I should drink an extra liter of water, they would say, why, don't you believe in the ability of your kidneys to work and to maintain homeostasis? So they get quite irked because they know that the gain of the negative feedback systems in your kidneys are very effective. There's hardly any error. Your kidneys are wonderful machines that were created by nature to maintain homeostasis over there. So that's an example of a infinite gain system to exist over there. Now, if we look at your negative feedbacks over there, usually, with the exception of kidneys, most of your feedback systems are not 100% effective. The responses are slow and incomplete over there. So and they take a little time. The change must happen first, and then after that you're going to get an effective response taking place. So that's why it's not such a good idea. I mean, it's there, it's good, but what's much faster and more effective would actually be your feed-forward system. So the feed-forward system, like I said, it predicts in advance and it makes changes in advance before anything could occur. So, and they're very effective. So So they cancel any steady state errors, and they do not provoke instability of a system. What does that mean? Well, remember your negative feedback system. Sometimes the gain could be so much, the compensation could be very high. There might be actually an overcompensation. So instead of bringing something back to a normal range, you actually overshoot the target and go totally in the opposite direction. So that's not a good idea also. We wouldn't like that. So this is how your feed forward systems are very effective. We have examples of feed forward system. I told you about thermoregulation. Then you have some with your eye movements, which we'll be talking about, and how we are able to compensate for changes in posture and eye movements. We'll reach those topics soon enough. Anyway, so with this we've done the concept of homeostasis. It's very important. It's the very epiphany of physiology, and if you know this well, you should be able to understand the very gist of like how every other chapter is structured around. It's about dealing with some parameter which we and how the body tries to keep it under constant conditions, and how failure of that leads to disease and pathology, and how so that's the whole chapter of pathology, how diseases take place. And then comes pharmacology, where we try to use medication to help these feedback systems to bring that parameter back to normal in very simple terms. So with this, I wish you the best of luck. Thank you very much, and I'll meet you in the next class.